Hello everyone. So we have started the etching process. We already have seen different wet etching processes. In the last lecture, we mostly covered the wet etching process. So as we have already discussed, that etching process can be divided into wet etching and dry etching. In case of wet etching process, we use different chemicals, and the chemicals that we use usually are very selective to the material that we want to etch. For example, say if you have a device, or say if you have a substrate, on top of that say there is a thin layer of silicon dioxide, then you need chemicals which will specifically etch out silicon dioxide and will not react with any other material present in the system. For example, if you use mask, then the etchant, the chemical that you want to use should not etch out the mask, or it should not react with the substrate, whatever is the substrate material. Say if it is silicon, then it should not react with silicon. So the etch rate, that is the rate at which the etchant will remove the material under consideration, should be high. So the etch rate for the thin film material should be high, and the etch rate of any other material ideally should be 0. That means it should not remove any material other than the material under consideration. So that is what we have seen, or we already have discussed. We also have discussed that there is a parameter called directionality as well. So usually we want the etching process to provide us features like this, where the edges are sharp. However, in practice, you'll find if you have mask over here, and if you do a wet etching process, you'll find there is certain sort of undercut, that is some portion beneath the mask will also be etched out, because the reactant or the etchant will react with the thin film material. Once it comes in contact with these sides, they will etch out the materials from the side as well, and it will create a undercut. So the process is isotropic. However, we need the process to be anisotropic, because usually when you design, you don't consider the undercuts. For example, if you design a MOSFET, then if this is the gate oxide, you want the gate oxide to be sharp on the edges, that is very straight. However, after etching, you may find that the gate oxide is something like this because of the undercut, okay, which is not desirable. So usually we want the process to be anisotropic. But in case of wet etching, it is very difficult to achieve a very good anisotropy. So usually wet etchings are isotropic in nature. Now, similar to wet etching, we also have a etching process which is known as dry etching process. Now, in case of dry etching process, we use charged ions to etch out materials. In this case, what you do is you take a chamber, closed chamber, you fill that chamber with gas, a certain gas, and then you use RF power in order to create plasma inside that chamber, similar to what you have seen in sputtering process. So there also you introduce argon gas, you energize those argon gas with the help of say RF power or some other power, and then you create plasma of that gas. Now once you create plasma, that plasma will contain various types of charged ions. That is what the ingredient, one of the ingredients of a plasma, because the atoms will be energized, they will leave out electron and they will become charged, the way we have discussed in case of sputtering. In fact, to some extent we also have discussed the same thing in plasma enhanced CVD. So these charged ions then will interact with the substrate and will take out the material from the substrate. So you have plasma inside this chamber, you keep your wafer or substrate over here, you use a heater also underneath in order to heat the substrate, and then the charged ions will hit this substrate, the surface of the substrate, and that charged ions will then etch out materials from it. Okay. So this is the usual process of dry etching. Now in this case, what is a plasma we would like to understand, because that will help us to realize what are the other processes. Like one process we already have seen in case of sputtering, that once there is a charged atom or charged ion, that will hit the surface and will knock out the molecule of that material. This is one way to remove some material from the substrate. Plasma also contains different types of radicals and different types of components that is reactive, highly reactive. So these reactive material also can come in contact with the surface and can react with the substrate material or the thin film material and can etch out that material by creating some certain sort of byproduct, right? So as we have discussed previously, plasma is the fourth state of matter. We have solid, liquid and gas, and then we also know the fourth state of matter is plasma. Now plasma contains electrons, ionized molecules, free radicals, neutral molecules, so on and so forth, so many components. Out of that, energized molecules, electrons, these charged molecules anyways will help us to etch out some of the material just by striking the substrate or the thin film material. Also there are free radicals present. These free radicals are very reactive in nature. They can come in contact with the thin film material, can react with that, and then they can remove the material from the substrate. The excited molecule supplies energy to the surface to be etched. So these are the process usually you can see in case of dry etch. Now free radicals present in the plasma are usually highly reactive and they have unpaired electrons in the outer shell. Usually the reactions are selective, that is the etch rate for specified thin film is higher than others. When there are a free radical which is present inside the chamber, they are usually very specific towards a certain material and they only will react with that material. So you will find the etch rate is considerably or significantly higher than any other materials present. Now the one of the examples of chemical reaction in dry etching process is the etching process that generally people use for silicon substrates. So what they do is they introduce CF4 gas inside the chamber, and then when they produce plasma of that material, then in that plasma they find CF3 radical which is very reactive in nature. So the CF4 molecule will be dissociated or will create CF3 radical, fluorine, and then one electron. This CF3 radical is again very kind of reactive, but the fluorine atom that comes out of one CF4 material will react with the silicon and will create SiF4 which is a gas. So the plasma, that is the CF4 plasma, will have a fluorine atom from each molecule, and that element will react with silicon and will create SiF4 gas. Now once they form a gas, obviously the gas will then come out as a byproduct and the same gas can be taken out using the gas outlet. So, there is a gas inlet and then there is a gas outlet. So, the gas outlet is used to take out the byproduct. So, in this way you can actually etch silicon substrate. So, this is one of the examples. There are many such examples present. So, just to give you an understanding that this plasma or dry etching process can remove materials from various substrates, or it can remove thin film materials from a substrate. Now, in this regard, there are two different terms that one should know. One is passivation, another one is sputtering. So, passivation is a process where you make a surface non-reactive. So, this passivation will ensure that the high selective molecules or radicals are not able to react with the surface because they are passivated. So, what people do is they actually create a layer on top of the reactive surface, so that this reactant atom or energized molecule is unable to take out the material from this side, horizontal side, and hence you will find most of the reactions are happening in the vertical direction. This is a very efficient process or very widely used process in order to increase the anisotropy. So, that will help us to reduce the undercutting inside the mask or beneath the mask, right. So, you will find this will give us an anisotropic structure. Now, one of the problem with dry etching process is because there are a lot of high energy molecules, they will also etch out different materials from different other areas. So, in that case, this passivation layer helps, and what people ensure is like the reaction taking place are very selective with the thin film material, right. So, we also have seen similar process in the sputtering, we have discussed the same. So, here also you will find that due to the formation of high electric field in plasma, the ions start hitting the surface, and which is known as sputtering. The same process you see in the sputtering process. So, this will also etch out the material. So, this energy transfer also increases the chemical reaction in the entire process. So, you will find that the sputtering is actually helping the chemical reaction that is happening between the other atoms, radicals and the thin film material, and this makes the entire process highly anisotropic. So, in this case the ions are removing the materials and hence the selectivity is low. As far as the sputtering is concerned, the selectivity is low because anyways these ions will hit other surfaces as well and they can take out materials from there. So, the selectivity for the sputtering is comparatively low. However, as there is a reaction involved, that will actually help us to maintain the selectivity, but the process is highly anisotropic. You will find very less undercut, especially if you take help of passivation. So, combination of both chemical and physical reaction is advantageous. Mostly in most of the cases, this combination is used in case of dry etching. Etch rate in this case is faster than both the individual processes that we already have discussed. So, the positive side of dry etching is the process is anisotropic. You can achieve high aspect ratio just by using dry etching process. You can also achieve complex features, especially if you want a high aspect ratio feature, for example, where the length is much higher than the width, or height is much higher than the width and other dimension. In such a situation, you will find dry etching processes very useful because the anisotropy is much higher, right. And this also helps us in achieving different complex structures. The selectivity is not very high, but it's fair. We already have discussed because the sputtering process is involved in this case. So, you will find that the sputtering process is also removing materials from, say, mask or substrate. However, in certain cases you can use passivation layer, or even if the sputtering process is there, because of the chemical reaction present in the plasma or the chemical reaction present in the entire process, this makes the selectivity towards the thin film much higher than that of the other materials. So anyways, the sputtering also transfers energy on the surface of the thin film, and that energy actually helps to increase the chemical reaction between the plasma and the thin film. So in a way it also helps or increases the chemical reaction. So this increases the selectivity in turn. Then less use of chemicals, so it's much safer. There is very less use of chemical. It's mostly depends on the plasma generation inside a closed chamber. So the risk of chemical spillage and etc., which was there in case of wet etching process, we explained the same. This process is much safer than that of the chemical process, and the process control is much better, because you have a control over RF power, that is the creation of plasma. If you want to create a specific plasma or a specific amount of plasma, you have a control over RF power, which can decide, or you can decide how much power is required for that. You have control over gas composition or gas concentration as well, how much gas you want to put inside the chamber. If you want to mix two gases, you can put two different gases inside the chamber for that purpose. Then you have a control over temperature as well, because you have a heater underneath the substrate, so you can vary the temperature in order to also make sure that the chemical reaction that is happening on the surface of the thin film can be controlled using the temperature control. However, there is some drawback of this particular dry etching process. One of these is like complex equipment. The equipment is not simple. It's similar to a sputtering system. It's a closed chamber, and then you have to ensure there are gas inlets and outlets, and then you also need to control the gas flow inside the chamber. You have to create you have to put or make an arrangement for RF power. You have to create plasma. So from the process itself, it's very evident that the equipment is complex. However, in case of wet etching, it's like chemical based process. So you just need some container and a suitable chemical agent. Then you can put the substrate or the thin film with substrate inside the chemical. Then it creates a lot of residues, just like other plasma processes. You'll find a lot of residues are there. There is a chance of contamination to some extent, but if you can maintain the gas outlets properly, that should not be an issue, but there is a chance. And the process is costly, because you can't create a large batch process, because it requires a closed chamber, and you can't create a very large closed chamber, because then you also need more gases. You need to have a better control over RF power and etc. So usually batch process is very difficult in dry etching. However, the dry etching can provide you anisotropic structures. That is one of the biggest advantage that you get from the dry etching process. Then the other process that we have discussed is doping. So in your electronic device courses or any courses related to electronic device, you already know that what is doping. It's addition of a specific impurity to a material, say semiconductor wafer, to modify its electrical property. That is the basic purpose of doping in semiconductor devices. So you can also dope other materials. It's not like only for the semiconductor devices or semiconductor materials. You can also dope some other materials as well. So the idea is to insert impurity into the material so that you can change some property of that material. It mostly is the electrical parameters or electrical properties. Sometimes the doping may also change mechanical properties. So doping can provide you or help you in tuning say mechanical as well as electrical properties. Now it's a very important process in semiconductor industry, because usually the semiconductor material that we use in industry, as of now, mostly it's silicon, and you need doped silicon in various devices, right? For example, in MOSFET also, you need to create source and drain area, which is a doped silicon or doped semiconductor, N plus or P plus, either it's highly N type or highly P type. Based on that, you choose which material to dope in that semiconductor material. There are two methods to dope a material. One is thermal diffusion, another one is ion implantation. These are the widely used methods for doping. And in case of thermal diffusion, from the name itself, it is very evident that you use temperature or heat energy in order to dope a semiconductor or any material for that matter. So what you do is you take the semiconductor substrate, and then the dopant molecules are there. Now once you heat it, they'll start diffusing inside the semiconductor material, and then the material will get doped. In ion implantation, you have ions present. What you do is you bombard the surface of the semiconductor substrate with different ions of dopant material, and then you can insert those atoms inside the semiconductor, and this is known as ion implantation. So in case of thermal diffusion, you'll find that the concentration of dopant atom is high on the surface or near the surface. So what you do in this case is you keep the semiconductor material inside say a high temperature furnace where gas of dopant atoms are present. Then they'll start diffusing inside the material, and then because they are diffusing, you'll find the concentration of these dopant molecules or dopant atoms are high near the surface. As we go deep into the surface, the concentration of the dopant material will reduce. So this is the typical plot for thermal diffusion process. Y-axis is the dopant concentration, and x-axis is the depth into the wafer, that is this particular axis, where this one is 0, the depth is 0. Here it's slowly increasing, the depth is increasing. So as the depth is increasing, the concentration is also reducing. Okay, so this is what the profile is. Near the surface, however, you have a high concentration of dopant atoms, because it's basically a diffusion process. So you'll find that the concentration near the surface is high, right? And slowly, as we go deep into the semiconductor material, at the end you'll find the concentration is same as base dopant concentration. If there is some base dopant concentration previously, then there will be the base dopant concentration deep inside the material. If the substrate is intrinsic substrate, so intrinsic silicon, then this base dopant concentration is basically 0, because there is no concentration of dopant atoms in the intrinsic silicon substrate, right? And similarly, you have ion implantation, where high velocity dopant ions are present. They come and bombard the surface of the semiconductor, and hence you will find that the concentration is high deep into the semiconductor substrate. So it's not near the surface, somewhere below the surface you will find the concentration is high. So if you look at the profile, you will find that the concentration is high somewhere, somewhere inside the material, inside the substrate material. It's not on the surface, because these high velocity ions are coming and hitting the surface, so they will penetrate the surface to some extent and then will get stabilized. So high concentration can be achieved at certain depth, not on the surface. So this is the profile for ion implantation process. But in this case also, you can see that if you want to dope a specific area of the semiconductor, you should use a mask, so that the material is diffused or implanted in a particular region, not throughout the substrate. But in case of diffusion or ion implantation, you'll find that some certain sort of or a few atoms will also diffuse beyond that range because of the thermal process or ion implantation or implantation process. It's not like very strict edge. There will be certain sort of distribution beneath the mask as well, but the major distribution will be where the opening is there. So you also use mask similar to your lithography technique or etching process. You can use a mask if you wish to dope a certain area of the semiconductor, and in fact it is required because in MOSFET you will find you need doping only beneath the source and drain region. So in order to create the source and drain region, you need to dope certain area of the semiconductor, not the entire semiconductor. So that's why in this process also requires mask. So there are 3 take-home messages. The first one is etching are of 2 types. One is dry etching, one is wet etching. So in case of wet etching, you will find the process is isotropic. There will be certain sort of undercut beneath the mask. In case of dry etching, the process is highly anisotropic, so undercut will be very less. In fact, you can take help of passivation as well, as we have seen in the discussion. Then passivation is a process to make the surface non-reactive. That is, if you have a surface, you create a layer of some other material which will help to protect this particular surface, even if it's a doping process or if it's a sputtering process that is there in dry etching. It will not come in contact with the actual material, and hence the thin film material will be protected. This is what we call passivation. Then doping can be done using thermal diffusion and ion implantation. We have discussed what is a thermal diffusion, what is ion implantation in brief, so that you get an idea about the doping process as well. So in the upcoming discussion, we'll see some of the material characterization, for example, say microscopy techniques. So microscopy techniques again can be of 2 types. One is optical, another one is electron. We'll see both of these microscopy techniques and how these processes help us to characterize different material or substrate or surface or device. Till then, thank you.